Yeah, thank you very much for the invitation. So for me, this is a sort of new community to speak in front of. So I'm very happy to be here, and I hope to tap into your knowledge a little bit. And so I will present some partially open problems or stuff I'm thinking about at the moment, and I would be very happy to discuss. So the title of the talk is Pluripotential Homotopy Theory. So homotopy theory, we will think about stuff like homotopy groups, and pluripotential here is just used in a very naive sense. So if there's any analysts in the room, please don't feel offended. So this just means like instead of considering solutions to the equation x equal dy, where d is the exterior derivative, I will consider equations like x equal dd bar y, the dd bar equation. Okay, so but let's start with some ordinary homotopy theory and a very old construction from the 50s by Massey. So let's take three cohomology classes, alpha, beta, and gamma, in the de Rham cohomology of some manifold. Okay, so they are represented by some closed forms. And then let's make the following additional assumption. The product of the first two classes is 0, and we remember a reason for why it's 0. Like this? Yes. And then the product of the second two classes should also be 0. And then we can form the following expression. We take the first representative times the reason, why the product of the second two is 0, and then plus minus the reason why the product of the first two is 0 times the last one. And if you compute d of this, you see that you get alpha beta gamma plus alpha beta gamma plus minus. If you put the right sign, this is again a cohomology class. And we've made some choices along the way. So we chose representatives, and we chose potentials here that make these exact. So if you do the math, this actually depends on the ideal generated by alpha and gamma. So this is well defined only in this quotient. Okay, so this way, let's give this a name, or a new symbol, triple Massey product. And we can consider this as a partially defined operation that takes three inputs and gives one output. And okay, I'm writing this slashed arrow here because it's not everywhere defined. We have some additional assumptions on the classes, and also the output is not really an element in here, but a set of elements, the whole class here. So this is a little bit awkward, and there are ways of getting around these awkwardness and getting overall well-defined operations that take three inputs, give one output. And okay, if there's a triple, you might imagine there are also higher operations. So there is a way, which is maybe called the theory of A-infinity algebras, to make this into a set of n-ary operations, one for every n, without any ambiguities, but then it gets technical. So let's just stick to this. Okay, so we have this thing, this new operation. What can we say about that? Maybe let me first give an example showing that it can actually be interesting. Maybe this is always 0. So I should separate these. Example, let n be the following. I will describe a three manifold, and I will describe it in several different ways. So for example, we could describe it as the S1 bundle over real two torus with Euler class, let's say Euler class, the volume class. Or if you prefer a more complex analytic description, we take the complex line bundle, which has first Chern class, the volume class, and then you take the unit vector, unit field bundle in there. Or this is also more topologically minded. You can look at the Hopf vibration S3 over S2, and then you can look at S1 times S1. This has a map to S2 by just collapsing all cells but the top cell, and then take pullback, or you take a quotient of group real and integral points of the group of upper triangular matrices. And that's also a description of this N. So if you get bored, you can check that all of these agree, and then you can also check the following. Then X, Y, Y in the cohomology of N is not 0, where X, Y are pullbacks of the fundamental classes. Sorry, for the S1 factors. So this is basically by construction, it's a bundle over the torus. The cohomology here you know very well, and it's generated by two classes. And by construction, we made it such that if we pull back the product of these two classes, gives us the volume class. If you pull that back to the total space of the bundle, it becomes exact. And that gives you this, that there exists such a primitive, and then if you do the calculations, maybe it's easiest here, you see that this is actually not trivial. Okay, so I mean, I'm not doing the calculations, but from this you will be able to work it out. Okay, so these can be non-trivial, but I'll be interested in some sense in a situation where they are trivial or maybe trivial. So how can we decide if they are all trivial? So let's step back a little. If we have a manifold, then we can associate to it the complex of differential forms, which also has an algebra structure. And then together, this is a commutative, in the graded sense, differential graded algebra. CDGA for short. Commutative differential graded algebra. And then from that, you can take, just using the first operation, you can form the cohomology, equip it with a zero differential, and still give it the induced product. So we can also consider this maybe slightly artificially as a commutative differential graded algebra. And then let's make the following definition. X is called formal if these two CDGAs are, and now I want to say isomorphic, but of course, let's say we're on a compact manifold. This is way smaller than that one, but this is finite dimensional. This won't be, so there won't be isomorphic as CDGAs. But if we look at CDGAs up to quasi-isomorphism, so we form a new category where we just formally invert all quasi-isomorphisms, then we can say this is actually isomorphic. And let's call this the homotopy category of CDGAs. Whoops. And this is the definition. So in more down-to-earth terms, sorry, AX as a CDGA, it's the space of forms. smooth forms. Differential forms. Thanks. Okay, so concretely, there is a chain of quasi-isomorphisms that goes from AX maybe to some C1, some C2, and then ends up at the homology. And then a little, very little lemma shows if X is formal, then all messy products are zero. So it's a little lemma to see that to compute these messy products, you only care about the quasi-isomorphism type, including the product. So we have used more than the ring structure here because we took primitives. But still, if you know the thing up to quasi-isomorphism, you can compute your messy product. And here, the differential is zero. So if we plug this in, this definition here, then the only way we can take primitives is by taking the zero primitive. Okay, so then all messy products have to be zero. Okay. This is, if we have this property of formality, then all our products vanish. Or put differently, yes.
So, if you like restrict the dimension of the DGA or of say X, is this like a classification? Is the messy product vanishing a classification of formality? Like how far is formality from all messy products vanishing?
Yeah. So if you take these naive messy products I described here, then it's just an implication, except maybe in very special cases. But if you use the conceptual thing that I've just hinted at, that you can talk about A-infinity algebras, then this is an equivalence. So the slogan is, if they all vanish uniformly and not just for some stupid reasons, then it's formal. Okay, and also not only the triple ones, but for all higher ones. Okay, so some easy examples which you can try to prove to get bored. Spheres are formal. We can actually literally write down a map from the cohomology to the space of all forms, which is a quasi-isomorphism and the map of algebras. Then connect sums and direct products of formal spaces are formal. So already from these two, we see, for example, that if we take S1 times S2 and then to connect sum with itself, and that is formal, so it has no products. But this thing, again, little exercise, has the same cohomology as the N over there. So we see these higher products can help us distinguish spaces that have the same cohomology. Oh, there's a statement missing. Is formal. All right, and now slowly, I mean, so far there has been a vector bundle somewhere hidden because the space of forms is maybe a space of global sections of a vector bundle, but to convert slightly to the topic of this conference, let's get to a more algebraic or close to algebraic things. And the example that makes this interesting for us here is the following theorem by Deline, Griffith, Morgan, and Sullivan that you're probably all aware of, or some is that compact scalar manifold are formal. So this puts huge restrictions on the topology of compact scalar manifolds. And because it will be relevant later, let me also remind you of the proof of this, or if you've never seen it, tell you about the proof of this. So compact scalar manifold satisfies the following equivalent conditions that you will recognize as the so-called DD bar lemma. And I want to give three equivalent characterizations of this. So first, let X be some pure type form. Then X being exact for D is equivalent to X being exact. Whoops. Yeah, that would be weird. So X being exact for the D operator is the same as X being exact for the DD bar operator. So yeah, one implication is always true, the other one is not true. So these are equivalent conditions. You could only remember this one, but maybe some others are easier to work with. The bicomplex AX. So, I mean, maybe I should have said this, even though probably everyone's aware of it, that you have this bigrading on the space of forms, and the differential decomposes into one component of degree 1, 0 and one component of degree 0, 1, if you have a complex manifold. So this is a bicomplex, essentially a complex of complexes, just that the two differentials anticommute. This bicomplex is a direct sum of squares, meaning bicomplexes of this type, and dots, meaning bicomplexes of this type. You just have a one-dimensional vector space in some degree, no differentials whatsoever. And of course, we can put these in any degree. And then third doesn't fit here. Third, the maps from what Chern cohomology of X. So what is this? Is the kernel of del intersect with the kernel of del bar modulo the image of del bar. This has well-defined maps to Dolbeau cohomology and also to the Ram cohomology. Thanks. And this again maps to so-called Epley cohomology of X. This is the kernel of DD bar modulo the image of D, but the image of D bar. All these maps which are just induced by the identity. If I have a form that's closed for del and del bar, certainly declosed, I have a map. Check that this is well defined. All the other maps work the same. All these maps are isomorphisms. So this first statement here tells us if you have a map go from here to here, this map is injective. If something is D exact, it's also DD bar exact. And that already implies all these maps are isos. Okay. And then just from here, we can take our space, our CDGA of all forms. We can look at the subspace of kernel del bar, equip this with the differential D del. This is again a CDGA. Then we can go to the Goethe homology of X by just projecting, equip this with 0 differential. Then this receives a map from the Bochern homology, and this goes to the Ram homology of X. And all of these maps are isomorphisms. Quasi-isomorphisms, sorry. These ones are isos. Okay, and that's the proof of formality. So one should note that the only thing we actually used here is the DD bar lemma. We didn't really use Kähler. We didn't use Hart-Lefschetz, for example. And there are many more manifolds that satisfy the DD bar lemma than compact Kähler manifolds. So this sort of applies a little bit more generally. Okay, and
the harmonic forms the same. If you went to like hard decomposition stuff, you get a hard.
come again?
I'm asking if are the harmonic forms the same of the map?
No,
No.
no, unfortunately not. I mean, yeah, then this could be made easier.
Right.
But in general, so there's a notion of geometrically formal, which is what you were asking for, maybe implicitly, is that the harmonic forms are already in algebra. And with Kähler or without Kähler, this is generally very restrictive and it enforces way stronger topological restrictions. So yeah, here it's in general, it's not true. That's a very natural question. For example, if you're on the Riemann surface, holomorphic one forms are harmonic. If you have genus at least 2, then every harmonic one form has to have a 0. Otherwise, you can see that you would fiber over a circle. But if you take the product of a harmonic one form and a suitable conjugate, sorry, a holomorphic one form and a suitable conjugate, you get the volume class. But you will always have a 0 because every holomorphic one form has a 0. So it cannot be actually Kähler class, a Kähler class. So already Riemann surface of genus 2 or higher are not our counterexample for this. Good. So maybe I should have said, okay, why do we care about formal manifolds? So one reason, of course, it's just some topological obstructions, and it's interesting, does this extra structure of having a complex manifold or a Kähler manifold imply topological obstructions? Formality is interesting because of the following reason also, I mean, related. So there's the following theorem by Sullivan, and I'm going to state it vaguely. For X simply connected, and you can do better than that, but I don't want to get technical. AX together with its product and the differential knows about the higher homotopy groups up to torsion. So what does this really mean? i.e., there is an algorithm to compute the higher homotopy groups of X, cancel the reals. So these are ideal groups to do that from AX. And even, I'm not going to write this, you really only need AX up to quasi-isomorphism. Okay, so this is all still old stuff. This is from the 70s. But of course, as a corollary of this, I mean, as a corollary of what I said just in words, namely that you only need the quasi-isomorphism type for X formal, you can compute the homotopy groups from the de Rham cohomology rings. Still simply connected. So yeah, this is nice. And this algorithm is, if you know your manifold well, you can do it. And it involves building, replacing the CDGA by some other CDGA that's sort of, one technical term, cofibrant in an appropriate model structure, and from that you can read off the homotopy groups. Anyways, this is just maybe a motivation. Why do we care about this formality? Good, and now I want to clean the board. Are there questions while I clean the board?
Does the corollary say that the fundamental groups are easy?
No.
Not easy to compute, but you know, nice group.
No, so in here the assumption is if the fundamental group is trivial. So if it's non-trivial, then in general, so you can generalize simply connected to nilpotent fundamental group. But if you don't have that, then this whole theory is not so well behaved. So maybe it's rather saying if you have very complicated fundamental group, you need some other tools.
I'm talking about the higher one.
Ah, okay. Okay, then can you say your question again? If they are simple?
Yes. Simple in the sense that simple to understand, like all
they are commutative anyway. So only the pi1 is non-commutative, and the higher ones are always commutative. So in some sense, they're already very simple. We're on a compact, simply connected manifold, so they are finite type abelian groups. They're determined by their rank and the torsion, and this allows you to compute their rank. So it gives you a lot of information about it. It somehow says, so you can think of a formal space as somehow the simplest space with the given cohomology ring. And it says that scalar manifolds are the simplest spaces with that cohomology ring from a homotopical point of view. Okay, now
ask a follow-up question?
Yes, please.
Does that currently mean that you can somehow kind of dispense with the manifold altogether and just start with, there's some purely algebraic procedure that starts with the homology and produces the ring? That it doesn't, it's almost like there's no more topology at all.
Yes, so what underlies this theorem is basically saying, so you can look at spaces up to homotopy equivalence. And we're forgetting a little bit of information here because we're forgetting torsion. We're tensoring with R. But you have a notion of rational homotopy equivalence, where you say a map is a rational homotopy equivalent if it's a homotopy equivalence in homotopy groups tensor Q or tensor R for that matter. So, and then you can localize at these maps. And there's a slight subtlety of Q versus R. Let me ignore that. That spaces up to rational homotopy equivalence are classified by the homotopy class of their algebras. Now you have to say what is the algebra of forms if you want to do this over Q, and then you have to bring in more technology, and I don't want to avoid that, but modulo this issue, it's yes, there is a reconstruction procedure that if you know this with the rational structure, you can reconstruct your space up to rational homotopy equivalence from the algebra of forms, and if you're formal, then you can reconstruct it from the cohomology ring. Yes.
Yes, I have a similar question maybe because you have an algorithm, but can you really effectively compute it from those informations? You have an algorithm, okay, but is it in any sense effective that you really can compute something?
That depends a lot on how you present your manifold to me. So there are many manifolds or also other spaces that, yes, one can do this very effectively. But there are also many ways to give me a manifold, and then there might be
let's say
the effectivity might depend on that a lot.
I give you the like the CDGA, not manifold, but
The CDGA. Yeah, then you can do it. Yeah, that's better. Yeah, then you can do it. Then a computer can do it.
oh, okay.
Yeah.
And this is orthogonal?
Yes, so there's also some subtleties going on. I mean, there is a functorial way of doing this, but then everything gets infinite dimensional because you want to do stuff without making choices. And there is a way that keeps finite dimensionality. That's not really functorial. Because you have to make choices. So in this algorithm, you will pick bases. Okay, so now we still have the definition of, maybe put this one up again. We have the definition of ordinary messy products, and we have the definition of these maybe slightly weird cohomology groups, the Bott-Chern and Epley cohomology groups. Now let me give you a definition due to Daniele Angela and Adriano Tomasini that's very much inspired by this one, of some kind of higher operations that depend on the complex structure. This was a purely topological thing. ABC messy products for Epley and Bott-Chern. And the definition is quite analogous. So you take, let's say, X now, and for the rest of the talk is a complex manifold. And then you take three forms, alpha, beta, gamma, and I want to assume them to be of pure pi degree. I would also there, I sort of suppress the degrees, but let's assume we have stuff of pure degree. And I want them to be del and del bar closed. In other words, to give classes in the Bott-Chern cohomology of X. And let's also assume that alpha beta, the product of these two, is 0 in Bott-Chern cohomology, which now means that they're DD bar of some X and beta gamma DD bar of some y. And then we can define, just as before, can form alpha y minus x times gamma. And if you check, this will generally not be D closed, but it will be del bar closed. And here we can actually always take a minus, in case you've been wondering about that. So alpha beta gamma minus alpha beta gamma. We apply the differential twice. So this is an element in epicohomology, which was some portion of the kernel of DD bar. Let's say this is alpha gamma A, B, C. Okay, set this, but I should write it. This is by Daniele Angela and Adriano Tomasini. They wrote down this definition and studied this in some examples. So of course, the definition is an immediate analog of this. Note some subtle differences. So if we look at the degree of this operation here, this one has degree -1 because we took primitives once. We're not just taking summing the degrees of the elements. This has degree -1. This one here has degree -1, or total degree -2. So it's really a different thing than that. Even though on a compact Kähler manifold, by what I told you here, we can identify both Bott-Chern and Epplich cohomology with the de Rham cohomology. So even on compact Kähler manifolds, these are a priori different operations. Okay, so this gives again, partially defined operation from Bott-Chern cohomology to Epplich cohomology of degree -1. And here's I think, intriguing question in view of this theorem of Deligne, Griffiths, Morgan, and Sullivan. Namely, are all ABC massive products trivial on compact Kähler manifolds? Before I say more on this question, let me just correct here that again we have an indeterminism, just as before. Okay, are all Epplich, Bott-Chern massive products trivial on compact Kähler manifolds? And this is actually surprisingly an open question, and which is basically what I maybe also want to motivate people here to think about, because I think there are some interesting testing cases where one can check this, like toric. It's known for projective space, they vanish. It's known for tori, they vanish. Basically, our knowledge stops there. I will say a little bit about this now, what we know. No. But possibly because no one has ever thought about this. I mean, this may or may not be hard. But I thought this is the right crowd to motivate for. Okay, of course. So maybe I will spend a little bit of time to reformulate this question in a more conceptual way, namely give a suitable analog of the notion of formality. Because right now it's this hands-on thing, I mean, which is nice to check explicitly. You can often compute these cohomologies and just do these calculations. And then you can say, okay, this one product vanishes, but you want some more conceptual thing to work with. So maybe I clean the board again. Another one. maybe first I should say, give you an example again without doing the calculations, saying that these can be non-trivial at all. Maybe we just did something weird and find 0 in a complicated way. So example, let n tilde be quite similarly defined to our manifold before, be upper triangular matrices with complex entries, modulo upper triangular matrices with entries in the Gaussian integers. This fibers over a complex two torus. And then that eta I be, let's say this map is P star of dzi, which dzi bar. So just yes.
I don't quite understand that quoting. That's somewhere.
Oh, sorry. Square. Okay. Thanks. Yeah. Fair point. Thanks. Okay. Let's pull back the two volume forms here, and then eta 1, eta 2, eta 2, ABC is non-zero. So in this example, you can compute quite explicitly, and you can check that this is true. Okay, this thing here is not scalar, and it doesn't even satisfy the DD bar lemma. It's so-called Iwasawa manifold, and it's one of the standard examples for stuff not to satisfy the DD bar lemma. But this example has recently been upgraded by Sferuzza and Tomasini. So the same Tomasini is there. Adriano Tomasini, and Sferuzza is a PhD student of his. Which says there exists a DD bar manifold with a non-vanishing ABC triple Nancy product. So this is good evidence that this question might be interesting, because remember, in the proof I just showed you, the DD bar lemma was the only reason why all of these topological Massey products vanished. And this does not imply formality anymore.
Explicit construction.
Yes. So the idea is to take this manifold, quotient out a finite group, to basically kill the cohomological weirdness that obstructs it from being DD bar. Then it's singular, and then you resolve the singularities and you keep the DD bar lemma while doing so, and you also keep the Massey product. So it's the same Massey product as here that survives. But it's not scalar. Doesn't satisfy hard Lefschetz. Too bad. Okay, but maybe indicating that this is a non-trivial question. So we need a different proof, and you can also check in maybe another little thing to do is to check that this proof breaks down after I have told you what the appropriate notion of formality is that we would want to prove by that. Okay, so, and yes, I've said this in words, so maybe let me not write it down. But let me say it again because it was sort of in the conversation. It's known for projective spaces and tori that this vanish is also known for Hermitian symmetric spaces. So for some spaces, it's known that all these products vanish. Right. So to give now a notion of formality, we need first a notion of the quasi-isomorphism. So let's give that definition a map F from A to B of bicomplexes. So ignoring multiplication so far, just bigraded vector space with two differentials, anticommute, is called a bigraded quasi-isomorphism if Bauchern cohomology, or the induced map in Bauchern cohomology and the induced map in Eppli cohomology are isomorphisms. So natural definition, if we want to deal with this, I want to make the point that it's also natural definitions from other points of views, because of course, if you have a bicomplex, you have many natural definitions. You still have a total cohomology. So you could just look at total quasi-isomorphisms, or you could look at row and column isomorphisms. So you have various choices to make. And then there's this result about that, which is by myself, maybe not too hard, which is that a map is a bigraded quasi-isomorphism if and only if it is an isomorphism in the derived category of bicomplexes. So what this means, let me just say it roughly, is bicomplexes where you quotient out squares, meaning a map is 0 if it factors over a bunch of squares like we had over there. Yes.
This implies that the total complexes are quasi-isomorphic.
Yes.
Because of this proposition.
Yes, exactly. So a corollary of that, okay, now I'm going to write here, so corollary F is a bigraded quasi-isomorphism that implies that the row cohomology, the column cohomology, also the Deram cohomology are isos. And really anything that factors over this derived category. So there are like more exotic cohomologies that you can think of for a bicomplex, and this thing will imply an isomorphism in all of these. In general, you might wonder, I mean, Dolbeault cohomology we know sort of better, why not work with Dolbeault cohomology? And so first of all, there is a real structure here. So you might want to work with Dolbeault cohomology and its conjugate, but many maps, if they come from geometry, they respect that real structure. So if they are Dolbeault quasi-iso, they are an isomorphism in the other thing as well. So if everything is bounded, if all our complexes are bounded, the converse holds. If you are an iso in Dolbeault and conjugate Dolbeault. If you're unbounded, this is not true. And if you, in some sort of more subtle parts of the theory, you want to pass to unbounded things. So this is maybe the more natural notion. But for many hands-on computations, it's enough to just work with Dolbeault cohomology. Maybe the takeaway. So let's just say converse is a little bit subtle, and I don't want to have it in detail. Now we have everything to make a definition of formality. Yes. So let's look at this object. It's a bicomplex together with a multiplication. So let's call it a commutative bigraded bidifferential algebra, CBBA, just like the PGA, just with bi. So if this one is isomorphic to, and now we have two options. Either we say to some algebra such that dB bar is entirely zero, or to some algebra such that B and B bar are entirely zero. Yes, thanks. In the category of CBBAs localized at bigraded quasi-isomorphisms. So again, explicitly, if it's just connected by some chains of multiplicative quasi-isomorphisms to an algebra, there's no DD bar, to an algebra, there's no differentials at all. Then X is called strongly or weakly formal. Maybe I would put it bigradedly formal, but then it gets long. Okay, then same lemma as before. X strongly or weakly formal implies that all these messy products vanish. And another little lemma says, so what, I mean, we have these two notions, it's a little bit weird. So certainly, if you're strongly formal, you're weakly formal. And from this, you can see the underlying space consists only of dots. There are no differentials at all. It's just a vector space, bigraded vector space. So it satisfies the DD bar lemma. And yes?
No, as I understand, so the first, on the top part of the board, the second condition appears to be strong.
Oh, yes. Thank you. Whoops. Yeah, that's stronger than that. Okay, so strongly formal implies weakly formal in the D-bar lemma, and the converse is also true. So this is the relation. If we think about our question here, we don't care about strongly or weakly because scalar manifolds satisfy the D-bar lemma. And it also sort of shows what is missing to get strong formality, because we still need this weak formality. Maybe there's some way to think about it. Okay, and I should say, maybe tell you about some non-trivial result of mine, since so far I've just motivated questions. So maybe let me also tell you what one can do here. So as a very modest step, maybe in the direction of this question, is the following theorem. It says that if X is compact scalar with the Hodge diamond of a complete intersection, so I just mean this naively. If you look at the Hodge numbers, just a bunch of ones, then something interesting happens, and then a bunch of ones again. It doesn't have to be the actual numbers that can really come from a complete intersection, right? It just only has cohomology in the middle, except from the Kähler class. So if that is true, and X has dimension at least 2, so we exclude Riemann surfaces, then X is strongly formal. Okay, so still a very restricted class, but still there's also a lot in there. For these, we know they are strongly formal, which is the stronger condition than just these products vanishing. The vanishing of these products you get maybe in a simpler way. Okay, that's I expect that the same method of proof can be extended to make the strip in the middle larger, but the same method doesn't work to make it arbitrarily large, as far as I know. Yeah, there's that. And then, as already said, there are sort of some standard examples that you can deal with. So let me stress open cases of this question, Riemann surfaces. This is, yeah, I don't know. So there could, in principle, I'm not saying I expect this to hold, in principle, there could be a holomorphic one form and an anti-holomorphic one form on a Riemann surface of genus at least 2, such that the product of 2 of these and 1 of the other, that could be non-trivial. And if you try to prove this, you end up with some integral equation where you want to see a certain integral is 0, and it's a non-trivial thing. I'm happy to explain that if anyone wants to think about that, but maybe I should leave some time for questions. So let me just see if I said everything else that I wanted to say. Yeah, sort of. I mean, maybe I say one more thing, also just in words. The class of this CBBA up to bigraded quasi-isomorphism, of course, remembers the thing we needed for Sullivan's theory, because bigraded quasi-isomorphism remembers total quasi-isomorphism. So it still knows about all the real homotopy information of the underlying manifold. So we have a forgetful map from CBBAs up to quasi-isomorphism to CDGAs up to quasi-isomorphism. And given a complex manifold, scalar or not, we can wonder about which CBBA structures can be put here on the given CDGA up to quasi-isomorphism. So for example, the theorem of Deligne, Griffiths, Morgan, and Sullivan says if the manifold was okay, this is sort of in the other direction. It restricts the thing down here. But I think it's so there is, of course, this big open question of whether there are any topological obstructions coming from the existence of complex structures. I'm not saying this will solve this, but it's a sort of a more refined version, because you can ask which algebraically, which things that algebraically look like complex manifolds, namely CDVAs, can be in the real homotopy type of a CDGA. And there are some results that are also more technical than I want to explain now, where I've already shown that one can say interesting things about the preimage of this forgetful thing. So there are obstructions that go way beyond the DD-bar lemma, where one can sort of say for certain homotopy types, you cannot have arbitrary complex structures on that homotopy type. Might have some, but they're sort of cohomologically restricted. Okay, so this is another interesting question, which is more technical. And now I stop. Thanks.